Hello everyone, and welcome to our 9.5a Intro to Trigonometric Ratios notes. And so that's a fun word to say. A lot of people will just shorten it to just trig. It's way shorter, but trigonometric is a fun word to say. We're going to be using trig the rest of this unit, and you'll be using this in many other math classes. You'll take a class called Algebra 2 with trig. You'll use trig in pre-cal. Trig is not something that's going to go away, and we introduce you to it. In this lesson, we're just going to focus on the ratios, the trig ratios. Tomorrow's lesson, we're going to start using it in order to find missing sides and angles of right triangles. So we've just learned about our special right triangles, the 45, 45, 90, and the 30, 60, 90. But not all right triangles are going to be 30, 60, 90, or 45, 45, 90. For instance, you might have a 40, 50, 90 degree right triangle. Or you might have an 87 degree, 3 degree, 90 degree triangle, okay? And so not all of them are going to be special right triangles. And we're going to need, this is going to give us a way to find missing sides and angles in non-special right triangles. So trigonometric ratios will be used to find missing sides or missing angles. So today we're going to focus on the ratios. Tomorrow we're going to focus on the missing sides. And then early next week we'll focus on finding missing angles of non-special right triangles. SOHCAHTOA, this phrase right here, is just a mnemonic device to remember the ratios of these things. So if you take out your calculator right now, if you look at the calculator you have, it has to be a scientific calculator, you're going to see some buttons that you've never used before. There's a button that says SIN. There's a button that says COS right next to it, and there's a button that says TAN right next to that. Those are going to be the buttons that we use whenever we're doing trig. Okay, what do those buttons actually mean? A lot of people mispronounce them as sin, cos, and tan. Those are just going to be, obviously those are shortened. They couldn't fit the entire word on the button, and so they cut off the E, so that's actually pronounced sine. Sine is going to be the ratio of the opposite over the hypotenuse. Cos, or cosine, is really how that's pronounced, is going to be the adjacent over the hypotenuse, and then tangent, TAN, is going to be the ratio of its opposite over its adjacent. And so instead of having to write that out every single time, what we're going to do is we're going to abbreviate it to SOHCAHTOA. And so that's just a phrase that helps you remember these ratios. And we're going to write that on almost every single assignment from here on out. I like to write it like this. We say the sine is equal to O over H. Cosine is equal to adjacent over hypotenuse, and then tangent is going to be equal to opposite over adjacent. So sometimes people will kind of write this out, opposite over hypotenuse, adjacent, that way it's just abbreviated, over hypotenuse, and tangent is opposite over adjacent. So this mnemonic device is going to be written at the top of almost every single one of our papers. I like to, when I write it myself, I'll write it like this, SOHCAHTOA, because that shows me the ratios and the order that I need to write them in. Okay, so let's start by looking at this triangle, just an overview. So before we even read anything, I have a right triangle. How do I know that it's a right triangle? Because angle C is a right angle, and by definition, a right triangle contains a right angle. If that is a right angle, then these other two angles, angle A and angle B, have to add up to 90, meaning both of those angles are going to be acute, because if they have a sum of 90, they both have to be smaller than 90. And so I can approach this triangle through the view of angle A or through the view of angle B. And so when I'm looking at this, what I want to do, what I want to do is that's my dog. I want to view this triangle first in terms of angle A, So it says to approach this triangle and to look at it, but look at it through the lens of angle A. Okay, so I'm going to put a little arc right here. That kind of looks like an eyelid to me, and it shows you who you're viewing the triangle through. So in terms of angle A, I have 3 side lengths listed on this triangle. I have variables there. I have a Z, I have an X, and I have a Y. So which one is opposite, which side length is opposite to angle A? So from opposite angle A would be side length Z. Okay. Which piece is the hypotenuse? Now that doesn't change no matter how we approach this triangle. The hypotenuse is always going to be the longest side. And so my hypotenuse is going to be Y. So this was my opposite. This is my hypotenuse, which forces the other piece that is touching the angle to be my adjacent side. So the adjacent is going to be your X. So the opposite is always going to lie on the side that is not touching the angle. And then the hypotenuse is always going to be opposite the right angle. It is the longest side. It's going to be touching one of these acute angles. And then our adjacent is going to be the other piece that's touching it. So you can see that yellow and green both touch the acute angle that we're looking at. So what is going to be my sine ratio? Well, sine is going to be opposite over hypotenuse. So when I'm looking at this in terms of triangle, in terms of the sine of A, in terms of angle A, that's what I want to look at. I'm going to zoom this in just a little bit so you can see a little bit better. In terms of angle A, opposite over hypotenuse, O over H, is going to be Z over Y. Z over Y. Cosine is going to be adjacent over hypotenuse. So what is my adjacent? It's X over my hypotenuse, Y. Tangent is going to be opposite over adjacent. So opposite over adjacent is going to be Z over X. Okay. So we have our opposite piece, we have our hypotenuse, and we have our adjacent. If you can label those every time, that is going to be extra useful whenever we're going through these problems. Okay? All right, this is the exact same picture, but now instead of approaching this triangle through the lens of angle A, we want to view this triangle through the perspective of angle B. So what changes? What stays the same and what changes? Well, first of all, we know that the hypotenuse is by definition always across from the right angle, so this is going to stay Y. The hypotenuse is still Y here. But what switches? The opposite and the adjacent are going to flip-flop because when you zoom into this triangle and you say, okay, well, what side lies opposite, that is going to be letter X now. And then your adjacent is going to be your one that's touching it. It's touching it, but it is not the hypotenuse. So we have our adjacent and our hypotenuse still framing the angle. The opposite is still obviously on that opposite side, but they interchanged. You can see that before it went Z, X, and then Y, and now it's X, Z, and then Y. So the hypotenuse stayed the same. The hypotenuse stayed the same. Okay? So let's see what that does to our sine ratio, our cosine ratio, and our tangent ratio. Let's see what changes. When I do sine, that's opposite over hypotenuse, opposite over hypotenuse. So when I do that, opposite over hypotenuse, for my new letters, opposite is X, hypotenuse is Y. So that becomes X over Y. Okay? Cosine is going to be adjacent over hypotenuse. So that's going to be Z over Y. And then tangent is going to be opposite over adjacent. Of course, my opposite and my adjacent switched when I went to angle B, so now this is going to be X over Z. Many of you noticed in class that, let's color code this, that the sine of A is going to match the cosine of B. And then the cosine of A is going to match the sine of B. And then this is interesting. The tangent of A is going to be flipped of the tangent of B, which makes sense since you interchanged your opposite and your adjacent. So you do not have to have that memorized, but it was just a pattern that we noticed that was very, very, very helpful when it came down to checking that we did that correctly. Okay, so that was in letters. Now let's look at the same thing, but in numbers. For angle A, we want to go in terms of angle A. So from the perspective of angle A, what is our opposite piece? Our opposite piece would be 6. Our hypotenuse, no matter what, is 10. And that forces the 8 to be the adjacent. So that is our values. Let's go through and actually calculate the sine of A, the cosine of A, tangent of A. And so when I do that, what I'm going to do is say sine is opposite over hypotenuse, so that's going to be 6 over 10. That is the ratio for the sine of A. But we know that ratio should always be fully reduced. So what does 6 over 10 reduce to? 3/5. And you could plug that into your calculator if needed. What is the cosine of A going to be? That's adjacent over hypotenuse. So 8 over 10, which is going to reduce to 4/5. Tangent is opposite over adjacent. Opposite over adjacent is going to be 6 over 8, which reduces to 3/4. So why are those patterns useful that we just discussed? This is 3/5, this is 4/5, this is 3/4. Why are those patterns useful? Because if the sine of A is 3/5, that means that the cosine of C from that other acute angle should also reduce to 3/5. So I can copy that to there. If the cosine of A is 4/5, that means that the sine of C should be 4/5. And the tangent is going to be where I take this and I do the inverse. So the tangent should be 4/3. But let me show you that just in case you did not recognize those patterns. You can always just go from the other point of view and find these same things without knowing that pattern. So from angle C, From angle C, our opposite would be 8. Our hypotenuse is still 10. Those stay the same no matter what. Notice that those are always the same. The hypotenuse doesn't change by definition, but we interchange our opposite and our adjacent. So this piece that is adjacent to C is now going to be this 6 right here. Okay, so what happens when I go to find those ratios? Notice this says of C, so my perspective's changing to C on these ratios. So from C, opposite over adjacent is going to be 8 over 10, which of course reduces to 4/5. Our cosine is going to be adjacent over hypotenuse, so 6 over 10, which does in fact reduce to 3/5. Tangent is opposite over adjacent, that is 8 over 6, which does reduce to 4/3. So we were able to find these pieces by knowing those patterns, and those patterns we noticed over time. Okay? All right, let's do that one more time with these values. This is our approaching this triangle first from angle D. Opposite would be 8. Adjacent would be 15, hypotenuse would be 17. The hypotenuse is always going to be the larger one touching the angle. But from angle F, different perspective, from angle F, opposite would be 15, adjacent would be 8, hypotenuse is still 17. So again, that does not change. But our opposite and our adjacent flip-flop because we're changing perspectives. Okay, so let's use the pattern on this one. If to find the angle D sine ratio, it's opposite over hypotenuse. That is going to be 8 over 17. That is fully reduced, so that does not change. Adjacent over hypotenuse is going to be 15 over 17. Again, fully reduced. Opposite over adjacent is going to be 8 over 15, which is also fully reduced. So how do I use that to find the sine, cosine, and tangent ratios of angle F, the other acute angle? Well, of course, we can just use that pattern. This one's going to be 8 over 17. This one's going to be 15 over 17. So we've copied that one here. We copied that one here. And then this is just going to be the reverse, which is going to be 15 over 18. So that's just an example of how the pattern makes it a little bit faster. All right, let's do this one more time. I want you to, with just whole numbers, and then we'll look at what happens when there's a radical there. Notice that this goes from x's point of view and x's point of view for sine and cosine. So that's where x is. To all of a sudden it changes to the tangent of z. So pay attention to the perspective, the ratio it's asking you for. So sine is opposite over hypotenuse. So from the pink one, that would be 12 over 13. Cosine of x is going to be the adjacent over the hypotenuse. That's going to be 5 over 13. And the tangent ratio of z is going to be its opposite from the blue one over its adjacent, which is 12, 5 over 12. Okay. So we changed letters, which made us change angles, acute angles, and that changed the perspective of the opposite. All right, let's do this one last time. Now, many of you noticed, it made me so proud. If you had to guess what kind of right triangle this was, you'd have to think back to the ones we've learned about, and a lot of you very quickly realized that this was a special right triangle, and the one it was a 30, 60, 90. And so let's look at this triangle and let's find the sine of D. So here's angle D. The other two are going to go from angle E. Okay, so I'm just paying attention. I like to color code it from the beginning. So what is the sine of D? Sine of D should be opposite over hypotenuse. So that's going to be 5 root 3 over 10. Ratios have to be fully reduced. So what do I do with that 5, that whole number 5 over 10? That is going to reduce to 1 over 2. So that's 1 root 3 over 2. We know that there's an understood 1 there, so I can actually simplify that even more by taking out the 1. Root 3 over 2 is that ratio of the sine of angle D. So what is the cosine of E? Well, we know that it should be the same as the sine of D, but if you didn't pick up on that, go to the yellow one. The adjacent is going to be this piece right here. It's going to be 5 root 3 over 10, which we just simplified that, so I know that that's going to fully simplify to root 3 over 2. So again, those end up being the same. And so what's the tangent of E? Tangent is going to be opposite over adjacent. Now this one's a little bit trickier. That's 5 over 5 root 3. Remember that for a ratio to be fully reduced, it needs to be in simplest terms, and we cannot have a radical in the denominator. That's just one of our radical rules. So we rationalize our denominator by multiplying by root 3 over 3. That gives us 5 root 3 over 5 root 9. Of course, root 9 is a perfect square. And so I can rewrite that as 5 root 3 over 5 times 3 wholes. This looks crazy. It's just got a lot going on. This is 5 root 3 over 15. And then, of course, whole number 5 over 15 reduces as a fraction to 1 root 3 over 5. Over 3, I'm sorry, over 3. 1 root 3 over 3. And again, we're not going to write that 1 there. Like on an ACT, they're not going to have that 1. We understand that it's there, but to be fully simplified, we leave that 1 off. So that was the hardest one where you had to rationalize the denominator. But we are able to do that with our special right triangles and our non-special right triangles, finding these ratios. We will actually go through tomorrow and figure out how to find missing sides and angles using these ratios.